All right, good afternoon. Hope everybody's doing well. Yeah, good evening too. All right, so I had a request about gray codes, which we were talking about briefly on Wednesday with respect to Hamilton paths. I don't think there's anything in the homework that directly relates to gray codes. That was really just kind of an illustration of something we can do with Hamilton paths. Well, okay, let me pull up the homework. Let's see what we got here. Yeah, let's go through this anyway. So question one, constructing ways to represent a matrix. So draw an adjacency list, adjacency matrix, incidence matrix. So that's just those three representations. First one, list each vertex and show all the vertices adjacent to it. Second one is a n by n matrix for n vertices where you show which vertices are connected. And then the incidence matrix, you have one axis which is edges, another which is vertices, and you show which edges are incident to which vertices. And then here's an adjacency matrix for an undirected graph, so sketch the graph corresponding to that. Here's an adjacency matrix for a directed graph, so sketch the graph, but you're going to have arrows on each edge, and you may have pairs of vertices where you have two edges, one in each direction. You may have one edge, you may not have any. And then question four, sketch the graphs for these matrices, label the vertices in the first ABC, the second X, Y, Z, and you can label those however you like. And then the question is, are these graphs isomorphic? And there's no real good, quick general technique for doing that, but basically you want to know if there's a way to relabel ABC from the set X, Y, Z that would give you the same adjacency matrix, right? And they're small graphs, there's only 3 vertices in here, so by just sort of playing around with it on paper, I think you'll be able to find a mapping that makes them isomorphic. When we have arrows on the same line going in both directions, can we just leave the arrows off? No, draw both lines with arrows just to make it clear, at least for homeworks in this class. So yeah, for this one, just sketch out the matrices, eyeball them, see if you can find a way to relabel the vertices to make them look like exactly the same graph. And then if you find such a mapping, show me what that mapping is. In other words, show me what A changes into, either X, Y, or Z. Show me what B changes into. Show me what C changes into. And on this one, directed graph with vertices as shown. And so for each of these, tell me whether, moving from each vertex to the next in this order represents a path, what its length is it simple, meaning you don't go back over an edge more than once, and is it a circuit? So that's just playing around with the definitions. Can we do examples of matrices to graphs? Sure, we can do one of those. Question 6, is there an Euler path, which means that it's a path that starts at any vertex, ends at any vertex, but travels each edge exactly once? And if it's a directed graph, you have to follow the edge in the direction of the arrow. If there's a pair of edges, you have to travel both of those. And then an Euler circuit means the same thing, but you start and end at the same vertex. Simple means you don't cross the same edge twice, correct? And then for a Hamilton, you need for a Hamilton path, you need to visit each vertex exactly once. It doesn't matter which edges you travel or don't travel. For a Hamilton circuit, you have to visit each vertex once, starting and ending at the same vertex. And so either find one or explain in your own words why one can't exist. And then the last question is Dijkstra's algorithm, and we're going to go through another more detailed example of that today. building on this graph that we had last time. So let's see, doing a graph from matrix, examples of matrices to graphs. So let's just make a matrix. It's random. So I'm just going to label these vertices. I'll just call them A, B, C, D. And I'll put them somewhere on my paper. So this is perhaps reminiscent of drawing state diagrams. And so this shows us where we have edges. We have an edge from A to A, and we have an edge from A to D. I guess this is directed because I didn't make it symmetric. So I'll have an edge from A to A, and another one from A to A, and an edge from A to D. So that goes like that. B has an edge going to A. B also goes to B. This feels a little silly to draw both of these here, but that's okay. And that's the only thing that B is connected to. C connects to C. I like these, apparently. And C also connects to D. And then D connects to B. And it connects to C. And it connects to itself. So something like that would come out. It's a goofy looking graph. I don't know. I mean, if I see you do just something like that in a directed graph, yeah, I'll take it to mean that it's going in both directions. It's kind of extra redundant to draw both of those, so either way is fine. But for this one, where we're going from C to D and D to C, definitely draw both edges with the direction. And if you had an undirected graph, like that. So this says there's an edge between A and B, and an edge between A and D. This says there's an edge between B and A, which we already knew. Also B to B, so we've got a loop there, and also B to C. And then C is connected to D, and that should be our whole graph. I would not draw a loop with a 2 next to it, because as soon as you start putting numbers on edges, it looks like you're talking about a weighted graph, and that's a very different thing. So safest thing, but possibly redundant, is to draw 2 loops, one with an arrow in each direction. But if you draw a single loop and it's directed, I'll take it to mean both directions. Columns, then rows. I don't know if it makes a difference. So with a directed graph, you have to have some sort of notation. For example, it's going to, if I have something in this row and this column, it's coming from this vertex to that vertex, right? If I did it the other way, if I said it was coming from this vertex to that vertex, then all my arrows would be reversed. So there has to be some kind of notation there, but whichever way you do it, it's going to look the same. It'll just be different arrowheads. Undirected, there's no ambiguity because it's just an edge. Cool. Other questions? All right, so let's revisit Djikstra. So we played with this a little on Wednesday, and this was the graph we were playing with those weights shown. So let's go through Dijkstra's algorithm again, but I want to, in addition to finding the shortest path, in this case from A to H, I also want to record what that path is that gives us the shortest distance. And it's only slightly harder than what we did on Wednesday. We simply need to record the vertices that lead us to our decisions at each point. So remember our algorithm. Visit the starting node. That's how we begin the whole process. And then relax adjacent nodes. And then visit the closest node that we haven't already visited yet. So visit the closest unvisited node. I'm using the word node here to mean vertex. And just keep repeating that. Alright, so how does this work? We want to find the shortest path from A to H. Now if you just want to find the shortest distance from A to everything, then we do the same algorithm and we just continue until we visited every node. If we're looking for the shortest distance to a particular node, we can stop once we've visited that node, because at that point we know we have the shortest distance. But a lot of times we're looking for a shortest path from here to everywhere. For example, if you're making a video game and you have monsters chasing the player, right? You could find the shortest path from the player to each monster, and that would tell each monster which direction they should turn at that point to get to the player as quickly as possible. Let's see. Yes, this is for homework question 8. All right. So let's start from node A, and we're going to start off, we're going to seed the whole algorithm by visiting the starting node. So I'm going to circle a node once it's been visited. And since this is my starting node, I'm going to record a distance of 0. So let me put that in here, distance. And the basic setup is we're going to write a tentative distance next to each node, which says we know we can get here in at least this distance, at most this distance. We might be able to find a shorter path. Okay, but we're going to write down a tentative distance. So there's a preliminary step, add a tentative distance. Of infinity to each node. So worst case, the distance from A to B is infinity. Worst case, the distance from A to C is infinity, and so on. So we add these tentative distances. Alright, so that's our first step, and then we go ahead and we visit the starting node and we set its distance to 0. Once we visit a node, we'll circle it, and the distance that we have marked for that node, that's the best distance we can find. Okay, so let's jump into our loop. 2 steps, we just keep iterating over and over. Relax the adjacent nodes and then visit the closest node. So relaxing an adjacent node means, given what you already know about getting to certain nodes, in particular a distance of 0 to get to node A, is there an adjacent node that we can now get to in a better distance than its current tentative distance? In other words, I can get to A in a distance of 0. If I add 2, I can get to B in a distance of 2. Well, 2 is a lot shorter than infinity. So I'm going to do what's called relaxing that node, which means I'm going to change the tentative distance from infinity to 2, and I'm going to record the path that it takes me to get there. How do I get here in a distance of 2? Well, use whatever path it takes you to get to node A, right, which is just, start at node A, and then tack on a visit to node B at the end. So this is a silly step for the first iteration, right? I can get to B with a distance of 2 following the path AB. And similarly, I can get to A by going to node A for a distance of 0. If I add 1 for a distance of 1, I can get to node C. 1 is better than infinity, so I'll relax this distance and say I can get here in a distance of 1, and my path is A followed by C. Okay, that's it for the first iteration of relaxing nodes. And if you were doing this on a test, this would be a good time to leave this and make a copy of this and start writing a new version of this. Because as you make changes to this, right, unless you make it very neatly, it's hard to know what you did along the way. So I would take this and I would say, I've relaxed my nodes, make a copy of this, and then go on, visit the closest node and relax, and so on. So your best bet is what I'm trying to describe right now, which is make separate copies of this, right, each time that you're going to make a different change. So I started off by visiting this node and relaxing adjacent nodes. If I mark another node as visited and I start relaxing those and I turn that in, I have no way of knowing when you visited what, right? So yeah, you could try listing off on the side the order in which you visit these nodes. The problem is if you just do this all on one page and anything goes wrong, it's really hard to know if you were doing the right algorithm and made a simple mistake, or if you don't understand the algorithm. And same thing when you get to the end. If the answer is wrong, I need to be able to go back and see your thinking to understand, were you applying the algorithm correctly. So your best bet at this point would be, right, make a copy of this. And if I do this on a test, I'll give you multiple copies of the graph, right? So make a copy of this, and now we say, okay, let's visit the closest node that we haven't visited yet. Well, most of these nodes have a distance of infinity, but here's one with a distance 2, here's one with a distance 1. This is our closest node. So we're going to visit this node, so we circle it. And now we go back to step 1, relax adjacent nodes. Alright, 1 plus 2 is 3, so we can get here in a distance of 3, but that's worse than what we already have, which is a distance of 2. So we're not going to change that. 1 plus 12 is 13, that's better than infinity. So let's change this to a 13. And how do we get here? Take whatever path you used to get here, which was AC, and then add on this node is a D. Okay, 1 plus 1 is 2, that's better than infinity, so we're going to relax this to a 2. And the path, well, take the path that got you here, which was AC, and then add this vertex, E. 1 plus 8 is 9. That's better than infinity, so we'll relax this to a 9. And the path is this path, AC, plus this vertex, G. We're not going to go back to this node because we've already visited that. We're done updating that thing's distance, right? A has been circled, it's been visited. We're not going to change its distance, right? It's guaranteed it's not going to be shorter. Okay, just take a look at what we have right now. We have a lot of path information. We know that there's a way to get from node A to node G in a distance of 9. And the way we do that is go from A to C to G. 1 and 8 is 9. Alright, so visit the closest unvisited node. We have a node of a distance 2, 2, 9, 13, and a bunch of infinities. We can visit whichever 2 node we want. I think we did this one last time. Let's go ahead and do this one, just for variety. So I'll say, okay, I'm going to visit that node. It won't affect your final answer. You'll end up with a shortest path of the same length. Could be a different path if there's multiple paths of the same shortest length. Alright, so I'm going to visit node E. We'll go back to step 1, relax adjacent nodes. Okay, 2 plus 17 is 19. That's not better than 9, so we don't relax. And that's the only node that's connected to E that we haven't already marked as visited. So we're done relaxing adjacent nodes. Now we visit the closest node, step 2. So we have unvisited nodes of distance 9, 13, and 2, and then a bunch of infinities. So this is our closest unvisited node. We'll visit that. Now we go back to step 1 and relax. So 2 plus 3 is 5. That's better than 13. So we're going to remove this. We're going to say 2 plus 3 is 5. And the path to that is the path to here, which is AB, followed by D. This is pretty straightforward to do in code, right? We're relaxing nodes adjacent to B, so we know how we got to B, AB, and we know the distance too. So for each node that we haven't visited yet, that's adjacent to B, take this distance 2, add the length of that edge, get a number 5, see if that's better than your current tentative distance. If it is, record that new tentative distance and set your path equal to this path, followed by this node. So ABD in this case. So closest meaning the smallest tentative distance from the beginning. So we're only looking at these numbers here that we have for each node's distance. This is the distance from our original node A. So it's closest from the start. Alright, so we're relaxing nodes adjacent to B. So we found this node could get a smaller distance, so we relax that. And these nodes have been visited, so we're done with the relaxation step. So now visit the closest node. So total distance from the start, there's a 5, there's a 9, there's some infinities. So our closest node is here, that's D, and now we relax from D. Alright, 5 plus 1 is 6, that's better than 9. So replace this with a 6, and the path will be ABD, followed by G. 5 plus 2 is 7, that's better than infinity. So replace this with a 7, and the path is ABD, followed by this vertex F. And every other node adjacent to D has already been visited. So we're done relaxing adjacent nodes. So now find the closest unvisited node, and it looks like that would be G, which we can reach in the distance 6. Let's sanity check what we've got so far. This tells us we can get here in a total of 6 distance. We do that by going from A to B, that's 2, to D is 5, to G is 6. To get to node F takes us a distance of 7. And we do that by going from A to B is 2, to D is 5, to F is 7. Alright, so the closest node is G, so we'll visit G. And that guarantees that this is the best distance we can use to get to G. The shortest path from A to G is 6. Alright, so relax adjacent nodes. 6 and 12 is 18. That's a better solution than infinity. So we'll do 18, and the path is A, B, D, G, and then H. And that's it for adjacent nodes to G. So we go back to visit the closest unvisited node. That's F. And so we visit that, and then we relax adjacent nodes. And 7 plus 1 is 8. That's a better solution. So we'll replace this with 8. And our path is how we got to F, which is A, B, D, F, followed by H. Visit the closest node. That's this one, and that's actually the node we were trying to find the shortest distance to, so we're done. It's also the last node, so we've actually visited all the nodes. But at this point, we can say definitively, there is a shortest path of length 8 from A to H by going from A to B to D to F to H. 2, 5, 7, 8. Now there could be more than one path of length 8, but we're guaranteed there's no path with length shorter than 8. Alright, so that's Dijkstra's algorithm. It's very efficient. So this would be a great way to present your final answer, right? Where you have all of your nodes marked as visited. You have the distance and the path to each node, including the distance and path to the final node, right? And I can look at this and I can generally tell if you did everything perfectly correct, right? The tricky part is if there's a mistake, right, and this turned out to be, you know, a 9, it's hard to know, you know, when did this get crossed out, when did that get crossed out, when did that get crossed out, right? So the time sequence helps. But yeah, I don't think there's any specific general global notation for defining this. It kind of depends on your context, and usually you're doing this inside code, right? So you've got some function that's returning a shortest path, and you have some kind of structure in memory, like a matrix or something that, or a linked list maybe, that's recording for each vertex the distance to their, you know, the tentative distance and the path. This is a nice application for a heap, by the way, because this visiting the closest unvisited node, well, if you store all your unvisited nodes in a heap and you use a min heap where you store it based on distance, then the root of that heap is always your closest unvisited node. And when you visit it, you simply remove it from the heap. The next closest node will move its way back up, and so on. So you can do some of that heap work. But it's a little complicated because, a little more complicated because you're adjusting these distances, so you need to keep reheaping and so on. Yeah, you can definitely do heaps in C. I mean, we did them in C in a sense, right? You're not in 222. Yeah, so in 222 we talked about heaps. And you can actually implement a heap really nicely using an array, which means, you know, you could do it in Fortran if you wanted, or pretty much any other language. You could do it in MATLAB, and you can do them in Python. Excellent. But do you see clearly? All right, cool. So that's Dijkstra. And you will almost certainly encounter Dijkstra somewhere down the road in your university studies, because it's just a really useful algorithm. So questions about that? Cool.
So,
Yes.
we make a copy of the then current graph, like on the homework, we make a copy after we relax adjacent nodes and then visit the closest node and circle it.
Yeah, basically after you've done a pair of these statements, it can start to get ambiguous on one picture, so that's a good point to redraw the picture.
Okay.
And if I give you this on a test, I'll give you a number of copies of this, and you can just sort of fill in your information as you go, so you don't have to keep redrawing the graph itself. All right, awesome. So let's go on to talking about languages and grammars. So this is let's see, question 5C. It's a directed graph. You're told to go from a node to another node, but the graph isn't directed to that node. That's not a path. Yeah, for you to be following a path in a directed graph, you have to be moving in the direction of the arrows. So if you have to go against the arrow, or if there's not an edge with an arrow in the direction you need to go, then it's not part of a path. Cool, you're welcome. All right, so this is the last unit for this course, languages and grammars, and you'll take a whole course on this at a university, usually called automata theory or something like that. But this is a first pass over some of these concepts, and the study of languages is as old as computer science, probably, right? I mean, people in the 50s were convinced that they could use computers to translate Russian into English, right? And that this was going to help the intelligence community and so on. And it did not work very well. Now, Google's language translator works pretty well today, but it's got a little more horsepower than the machines we had 70 years ago. But people have studied languages, both in terms of, computer science implementation of algorithms, but also just kind of abstractly on their own. If you read any Noam Chomsky, in addition to his political work of more recent years, he was a linguist, and he studied a lot of things about languages and ways to analyze languages. And some of the terminology you'll encounter, there's things called Chomsky hierarchies and the Chomsky grammar and things like that. So it's a really rich area, and it's kind of innate to human curiosity to wonder about language, right? I don't really remember how I was taught to talk, but somewhere we learn this, and our brain does some kind of miraculous wiring of neural pathways, and we can form sentences, and we can hear sentences, and we can conceptualize, and it's all very kind of mysterious, right? To me, at least, and it's fascinating. So an important distinction in what we're going to talk about is syntax versus semantics. And semantics are really hard. Semantics is the meaning of a sentence, and we're not going to be talking about that. That's, where Google kicks in. That's where machine learning and AI and these kinds of things kick in. Trying to understand the meaning of a string of words is a totally different set of problems. We're not going to worry about that in here. We're going to concentrate strictly on syntax. So that, for example, we could take a collection of words and know, is this a valid sentence? And there are valid sentences that are completely ridiculous. So one of Chomsky's examples was, the sleepy, colorless green gas never sleeps. And that sentence has no meaning, right? You can't be colorless and green, and gases can't be sleepy, and so on. But syntactically, it's a perfectly valid sentence. Okay, so we're going to look at syntax. And this is the job of a compiler, right? A compiler does not say, oh, your code's not going to do anything useful. right? It doesn't care what your code's going to actually do. A compiler only cares, is this a valid C program? Do you have a semicolon after every statement where you need a semicolon? But it doesn't care if your program says something like, you know, if 1 is equal to 2, x equals 5, x equals 10, x equals 0, if x equals 11, you know, do something. Well, that's ridiculous code, right? Because first of all, 1 is never equal to 2, and if it was, setting x to 5 and then 10 and then 0 just sets it to 0. And if you just set it to 0, it's never going to be equal to 11. But there's no compiler out there right now that's going to look at this and say, you know, hey, what are you doing? You know, well, there are some that'll do it, but they're kind of annoying. But it'll compile this because syntactically this is correct, right? Now, if you leave off that semicolon, it'll say, hey, wait a minute, right? But it's just looking at the syntax. So we're going to do the same thing. We're going to look at the syntax of languages, and in particular, we're going to think about how can we describe what constitutes a valid string or sentence in a language, and how can we take a sentence and tell if it's valid under some sort of language specification. All right, so these can be called formal languages. And they're more formal than, you know, general human language where we can invent words or we can come up with weird, you know, 2-letter abbreviations because we're texting and things like that. So we want to study very formal languages. And let me give you an example. So I could define a language as follows. I could say a sentence is a noun phrase followed by a verb phrase. Well, I have to tell you what these things mean, so I'll go on further and say a noun phrase and say this is an article plus an adjective plus a noun, or it's an article plus a noun. So we could skip the adjective. And a verb phrase is equal to a verb plus an adverb, or could just be a plain verb. And an article is either the or a. An adjective could be funny or hungry. A noun is either a laptop or a bunny. A verb is hops or overheats. And an adverb is quickly or beautifully. All right, so there's a formal description of what it means to be a sentence in this bizarre language. It's a noun phrase followed by a verb phrase. And you can do two things with this. You can construct sentences, or you can take a set of words and ask, is this a sentence? Okay, how do we construct sentences with this? Well, that's called Mad Libs, right? If you've played Mad Libs, that's really all you're doing. You're saying, give me a noun phrase and give me a verb phrase, or give me an article, an adjective, and a noun. And you pick those words out and you plug them in, you put them together. When you play Mad Libs, right, you end up with complete sentences that are syntactically correct, but usually silly in their meaning, their semantics, which is what makes them fun. So yeah, the hungry laptop overheats beautifully. That's a perfectly fine sentence. The bunny overheats. That's a perfectly fine sentence. Right? But they're kind of like silly. So one way to do this is to, start from the bottom and say, okay, so an adverb is beautifully, and a verb is overheats, and a noun is laptop. And so my noun phrase will be the, followed by a laptop, so the laptop. And my verb phrase will be overheats, followed by the adverb beautifully. So the laptop overheats beautifully, and that's a sentence. The hungry laptop overheats beautifully. The other thing we can do is we can analyze a sentence and say, is this part of this language? And so this is like diagramming sentences, right? So when you diagram sentences, you could say something like this. This is a noun phrase, and this is a verb phrase. Right? And a sentence can be a noun phrase followed by a verb phrase. But how do we know that this is a noun phrase? Well, we may not. But here's what we can do. We can say this is an article, and hungry is an adjective, and laptop is a noun. And guess what? An article followed by an adjective followed by a noun, that's what we call a noun phrase. So this thing is a noun phrase. Overheats is a verb. Beautifully is an adverb. And a verb followed by an adverb is a verb phrase. And a noun phrase followed by a verb phrase, that's a sentence. And so this thing is a sentence. It's a bunch of things. It's also a noun phrase followed by a verb phrase. It's also an article, adjective, noun, verb, adverb. It's also an article, adjective, noun followed by a verb phrase. All right? And this has a natural tree-like structure. So the binary trees we've been talking about in 222, right? If we take away the binary part of it, and we just think of a general tree, which is like a graph, basically, right? We can describe a tree-like structure for this. And this goes a little bit in the other direction. So a sentence, for example, we can think of as a noun phrase followed by a verb phrase. And a noun phrase we can think of as an article followed by an adjective followed by a noun, and an article is the, and so on. And so this diagramming of sentences we can capture in a tree. And that's related to how we can do some of what we're doing on paper here inside a computer. And part of what makes this tricky is there's some ambiguity when you're doing your diagram, right? Maybe I have more than just a noun phrase and a verb phrase. Maybe I'm allowed to have two noun phrases. And how do I know if this goes with the first noun phrase or the second noun phrase? So with a very simple language like this, it's pretty unambiguous how we're going to take something like a sentence and break it down into these pieces. But a lot of times there's ambiguity, and we'll see that as we move forward. And this is where computers come in. For example, if you think about parsing the C language, right? Taking a set of C code and figuring out what each statement is doing, right? If I say integer I could be declaring an integer. I could be declaring a function named I, because I'm going to have a parentheses here, which lists a bunch of arguments. I could be initializing a variable if I have an equal sign after this. I could be declaring a number of things to be integers if I find a comma after this, right? So we don't necessarily know what we're seeing in a language until we look further into the input. So these can get a little more complex pretty quickly. But this is why we have computers. All right, so we're going to do a bunch of definitions now. And we're working our way up to a very formal definition of what we're going to call a phrase structure grammar. And a phrase structure grammar is going to be a way to describe a language. And we're going to describe it basically in terms of how we create things in that language. Okay, so let's build up to this, but there's going to be a bunch of definitions here. All right, so let's start with a vocabulary. And I lost half my recording from 222 second class, so I keep checking to make sure my recorder is still running, which it is. So let's start with a vocabulary. A vocabulary V is a finite non-empty set of symbols. Alright, so we're doing a set theoretic approach here. And by symbols, I mean, you know, letters, digits, characters, whatever we're defining. We'll have to specify that. But a vocabulary is a finite, non-empty set of symbols. So it's the things from which you build other things. Alright, a word or a sentence, we'll kind of use these interchangeably. A word or a sentence over V is a finite length string of elements of V. So when we talk about a word or a sentence over V, it's just a collection of elements of V, finite in length, so it can't be infinite. But it's a string, it's not a set, right? So the same symbol can occur more than once. So think of your vocabulary as being the ASCII character set, and then a word would just be, you know, a string of characters. Alright, we use the symbol lambda for the empty string, which is a string of 0 length, a string comprised of no symbols. And it's not the same thing as an empty set. Strings and sets are totally different creatures. So for an empty string, we use the symbol lambda. And it's a really, really useful symbol. Alright, we write V with an asterisk on top, and that's the set of all words over V. Let me put or sentence in parentheses, because I'll mostly stick to word. Okay, V star is a set of all words over V. So the collection of all finite strings of symbols from V. Alright, Suppose our vocabulary is the set of letters A through Z. Then a word over V is just a collection of letters. As long as it's finite in length, it could be any string of letters. And V star would be the set of all strings comprised of symbols from V. So basically, take a bunch of Scrabble tiles and just throw them on the floor and put them together in some order, and you've got something that belongs to V star. It's the set of all possible words. All right, so now we can define a language over V is a subset of V star. So it's some presumably smaller collection of strings of symbols from our vocabulary. So if we tried to apply this to English, and we don't really want to do too much going back and forth because human languages are so imprecise, but if we thought of this in terms of English, right, our vocabulary would be the set of letters A through Z. A word would just be some collection of those letters. V star is a set of all possible collections of letters. And a language might be the set of collections of letters that we find in the dictionary. So, this is a perfectly fine word. A language would be a subset of all of these, and it might include, this string and this string and this string. Right? And so the particular subset of words over V that we find in Webster's dictionary, that might comprise, the English language. So we're interested in this question of language, and how can we describe which strings make up a language? So specifying a language. So how do we specify the elements of a language? Well, one way to do this list all words. Right? Just list all the members of V star that are part of your language. If we tried to do this in writing a C compiler, what would we do? We would make a file on disk called, legal C programs, and we would simply list in there every legal C program. And then when you type in a program and you want to know, did I make any syntax errors, it would just compare it to every possible legal C program to see if it found it. And if it did, it's good syntax. And if not, there's some sort of syntax error. That would be a horrible way to write a C compiler, right? Because there's an infinite number of possible C programs. But for English, this is exactly what we do. This is what a dictionary is. You pull this book off a shelf and it contains a list of all the valid words over this language, over this vocabulary. So that's one way to specify a language, list all of the words. A second possibility is list rules for something to be a word. And we do this somewhat in English too, I before E except after C. Or usually a Q is followed by a U. Or every word has to contain a vowel, except for syzygy. It's like how if a monkey writes a bunch of words on an infinite amount of time, eventually the monkey writes Shakespeare. Yeah, right? So Shakespeare such and such is a subset of the set of all collections of words Alright, so this is another way to specify a language. List rules to tell you whether or not something belongs to the language. That doesn't work very well in English either. Right? There's a few rules by which we can say something is not a word. Right? For example, if I write, you know, this, we can probably say that's not a word because there's no vowels in there. Right? But that doesn't work in general. And it doesn't work very well for a lot of computer applications. So a third way to answer this question is to use a grammar. So describe a grammar. Yes, yes, grammar. So what is a grammar? It's a set of symbols, and it's a set of what we call production rules. So we're going to basically describe a set of rules from which we can create elements of this language. And this is what we're going to study. And in particular, we're going to study something called phrase structure grammars. All right, some more definitions. So a phrase structure grammar, G, is a four-tuple. So it's comprised of four things, three of which are sets. So V is the vocabulary. All right. What's a vocabulary? It's a non-empty set of symbols, finite in length. So V is a vocabulary. It's the thing we're building up words from. T is a terminal symbol. And there could be more than one. So terminal symbols. And this is a subset of the vocabulary. We'll do some lots of specific examples which will help. S is the start symbol. And that's an element of our vocabulary. And P, this is the fun part. P is a set of production rules. The production rules basically tell us how to change one symbol into another. All right, so let's do some examples. I'll leave that aside. So our grammar is this regular four-tuple. And let's suppose our vocabulary consists of the following symbols: little a, little b, uppercase A, uppercase B, and lowercase s. Our terminal symbols are comprised of lowercase a and lowercase b. Our start symbol is going to be this lowercase s. And our production rules in this example are going to be the following. So there's a rule which says S can be replaced with big A followed by big B followed by little a. There's another production rule which says A can be replaced with two uppercase B's. And there's a rule which says B, uppercase, can be replaced with little a, little b. And there's a rule which says uppercase A followed by uppercase B can be replaced by lowercase b. Alright, so this is a description of a phrase structure grammar. Vocabulary, terminal symbols, start symbol, which is S, and then production rules. And the idea is, if you start with the start symbol, you can apply any production rules to replace any left side with a right side. And so let's see what kind of words we can produce starting with the start symbol. Now, this is certainly a word over our grammar, but we're mostly interested in words comprised of terminal symbols. So these things like big A, big B, and S, these are sort of intermediate temporary variables. Alright, so we're going to start with the start symbol, we're going to apply production rules and try to come up with words, strings, comprised only of terminal symbols. And those will be the words over our grammar. So, well, we have one production rule which says S can be replaced with uppercase A, uppercase B, followed by lowercase a. Now what can we do from here? Well, we know that we can replace our uppercase A with two uppercase B's. So this could be replaced with, the A becomes two uppercase B's. We'll just leave the B and the little a over there. So from the start symbol, we can also produce big B, 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 little a. And we can also replace the large B with a lowercase ab, which means this could be replaced with AB, AB, ABA. And that's a string comprised of terminal symbols, so that is part of our language. Is there any other word that I could have gotten from our start symbol by using these production rules? BA, right? So we have a rule that says AB can be replaced with B, so we could have taken this AB and replaced that with a B, and then let it be followed by an A. And there's a totally different string of terminal symbols that we can get to from our start symbol. And we could also have kept that first uppercase A, but then taken this uppercase B followed by a lowercase a, or no, we could have taken this B and replaced it by a little ab, and then kept that last A, and then taken this A and replaced it by a pair of B's, and then taken each of those B's and replaced it with an AB. And we end up with the same string that we got on this branch of our tree. And I think those are the only possibilities. So this language consists of two words. Abba, Abba, and BA. And this is a bit of a hard problem in general, because any application of these production rules anywhere along the way can lead us to a valid word. And if we wanted to enumerate all the words that come from this language, we would need to know that we've covered every possible application of these rules in every possible situation. And that's, a divergent process. We're starting with a single start symbol, and we're trying to find every possible string of terminal symbols that can possibly be derived from that. We can do this on a computer pretty easily. And it's recursive, and it's stack-based, and it's not a problem to code this up. But for us as humans, we need to sort of keep track of, so we already used this rule over here, but now I could use one of these two rules. So let's follow this one and this one, right? And it's maze running and it's depth first search and all of that 222 stuff ties in here. All right, so that's an example of a particular grammar and looking at some of the strings that can come from that. And those are the only strings. If you try other combinations of these rules, I don't think you'll find any that take you somewhere else. So let's formalize this, and then we'll go through some more examples. So definition. So suppose we have some string W0, which is some string L, followed by some middle string Z0, followed by some string on the right called R. And suppose W1 is a different string, potentially, with the same string L, followed by a different middle part Z1, followed by the same string R. So W0, W1 are two strings that begin and end with the same stuff, but something in the middle is different. All right. If this rule is a member of our set of productions, in other words, if there's a production rule for changing this string, if there's a production rule for changing this string into that string, right, for changing Z0 into Z1, then we can say the following. We say W1 is directly derivable from W0. So if you have two strings, then you can express them in a way where the middle part can be changed from here to there using something in our set of production rules, then this string is directly derivable from that. For example, if we had a string ABA, well, let me make it BABA. We have a production rule which says uppercase AB can be replaced with B, which means this can be changed into B followed by a little b followed by an A. Right? So this is the left part, this is the right part. This middle part, there's a production rule, one rule for changing this into this. So this string is directly derivable from that string. So sort of the canonical definition of what you might think directly derivable means. And remember, strings can be empty. So if you have a string like ABA, right, we saw that we can change that first A into a pair of B's. So here's our original string. The left part is empty, that's the empty string lambda. The right part is this lowercase a preceded by an uppercase b. And the middle part, uppercase A, can be replaced by two uppercase b's. Right? So this string is directly derivable from that. So it's basically, what you get when you go down one level in this derivation tree. All right. So W1 is directly derivable from W0. If that middle part can be replaced, can replace that middle part above using something in our set of production rules. Okay, that's directly derivable, and we write this as W0 double arrow W1. Right, so we can turn this into that. All right, if there's a series of these direct derivations, like W0 can be changed into W1, and W1 can be changed into W2. And we can change, you know, into Wn, for example. Then we say Wn is derivable from W0. So not necessarily directly derivable, but through a chain of direct derivations we can get from W0 to Wn, we say Wn is derivable from W0. And we write that as W0 arrow Wn, but we put a little star on top of the arrow. And this is a derivation. Yeah, not at all unrelated to the proofs we were doing before. In fact, you could probably find a dual to propositional logic related to grammars. So ABA can be directly derived into BBBA, because there's a production rule for replacing AB with BB. On the other hand, ABA, there's a derivation from that into this string down here, because this is directly derivable from that, and that's directly derivable from that. Alright, so derivable just means a series of direct derivations. Okay, so here's our grand definition. This is what all of this is leading up to. So definition. The language generated by a grammar G or sometimes we say the language of G equals the set of all strings of terminals that are derivable from S. So it's a set of all strings of terminal symbols that you can get to by starting with S, your start symbol, and applying production rules. But formally we would say the set of all strings of terminal symbols derivable from S. And if we want to write that even more succinctly, L of G equals the set of all words in T star which are derivable from S. So there's a one-sentence description of the language generated by a grammar. So nice set theory notation there. All right, so that's the definition, but examples are probably more useful for nailing down what exactly we're talking about here. So let's do some more examples. So I'm just going to keep, you know, this idea in mind. Our grammar, I'm going to use V for vocabulary, T for terminal symbols. Start symbol is going to be S. The production rules will be listed explicitly. So let's do some examples. So let's set our vocabulary equal to S, uppercase A, lowercase a and b. Let's set our terminal symbols again to A, B. Our start symbol is S, and let's use the following production rules. So we can take our start symbol and turn it into little a, big A. We can take our start symbol and turn it into little b, and we can take a big A and turn it into a pair of lowercase a's. So what are all the words in our language generated by G? Well, we can do our tree type derivation, start with a start symbol, and we've got a few possibilities. One possibility right here, we could just turn this into B, and that's a string comprised of terminal symbols. So B is certainly part of the language. The other thing we can do with a start symbol is we can turn it into a little a followed by a big A. And a big A can be turned into two little a's. Now this is not part of our language because it's not comprised of terminal symbols. Right? Big A is not a terminal. But we can replace the big A with two little a's. And now we have another string of terminal symbols. And that's pretty much all we can do. So this is a pretty small language too. We're going to spend a week playing with the stuff in this topic, but we're not going to have a chance to do homework, turn it in, get it graded, get it back to you, and discuss it. So most likely questions on this unit are going to be sort of higher level conceptual. But we'll see what we get through and what kind of questions we run into. But it's going to be pretty light if any of this pops up. But I don't want you to tune out. This is all good stuff. But don't panic as far as the exam, because I don't like giving exam questions when we haven't at least done, you know, some of the similar material and graded exercises that we've been able to talk about. So this is like almost freebie stuff. All right, let's do another example. Let's make something a little more interesting. So let's set our vocabulary equal to 0, 1, big A, big B, and S. Our terminal symbols are going to be 0, 1. These are very common terminal symbols for us because we can write binary numbers out of this. And binary numbers are a great source of questions about languages. So our start symbol is S, as it almost always will be. So here's our production rules. So we can take S and turn it into 0A. We can take S and turn it into 1A. We can take A and turn it into 0B. We can take B and turn it into 1A. And we can take B and turn it into 1. Alright, so we're doing analysis at this point. We're looking at grammars and we're trying to figure out what things are part of that language. Monday we'll start in the other direction where we'll do synthesis. We'll start with a language and try to write a phrase structure grammar. But let's just do analysis first, because this will help us get more familiar with working with these concepts. So what are some words that are part of this language? We can start with an S, and we can apply any of these production rules. So for example, S can be either a 0 followed by an A, or a 1 followed by an A. And there's only one rule for translating an A. A becomes a 0 followed by a B. So if I've said that S changes into 0A, well, that A is going to be a 0 followed by a B. And here it's a 1 followed by an A, well, that A has got to be a 0 followed by a B. So what are some strings of terminals that are part of the language? And you should be able to see a few of them right now. Right? 0, 0, 1, because B can be replaced with a 1. So there's a word in the language. Good. 1, 0, 1, because again, B can be replaced with a 1. We got the sirens of jubilation for string recognition. So 101, that's another word. All right. Any other possibilities? Cue the sirens for the win. I live right next to the firehouse, so hopefully that's not an actual fire. Hopefully it's just a cat up a tree. What else can we do with this? Are there any other words? Yeah, so this B could be replaced with a 1 followed by an A, so 0, 0, 1A. And similarly, 1, 0, 1A. Well, again, an A can only be replaced by a 0B. And you can see where we're going now, right? We've got two possibilities. That B could be replaced by a 1. And so now we've got another pair of strings in our language. But this B could again be replaced by a 1A. And so we're going to have two possibilities under here. There's an infinite number of words in this language. We can go on forever. But each word is going to be finite in length, right? It's not a word otherwise. It's a finite length collection of symbols. But we can probably start to notice a pattern if we do a few more of these, right? So this one will take us down to 0, 0, 1, 0, 1, 0, 1, or 1, 0, 1, 0, 1, 0, 1. And so it's basically a 0 or a 1 followed by a collection of 0 1s. I think I messed this one up. So it's an infinite language, but it's described with this very finite set of information. Vocabulary, terminal symbols, start symbols, and a handful of production rules. And so this we would end up writing as 0 followed by 0, 1 to the n bigger than or equal to 1. Where this doesn't mean exponentiation, it means repetition. So it's a 0 followed by 1 or more repetitions of 0, 1, or it's a 1 followed by 1 or more repetitions of 0, 1. All right, we're out of time, so we'll play more with this on Monday. We'll look at some grammars and look at the language generated by those grammars, and then we'll flip this around and we'll say, given a language, how do we come up with a grammar? And this is like the difference between state machine analysis and state machine synthesis in 250. The first direction is a little more straightforward, and it prepares you for the reverse direction, where you start trying to generate these production rules to correspond to a particular language. So we'll play around with that on Monday, and then we'll look at a few other ways to represent languages. We'll look at something called BNF, Bacchus-Naur form, which you can actually use to represent, a programming language, for example, pretty succinctly. And then we're going to loop back and talk about finite state machines. And I promise you we won't draw any state tables like we did in 250, but we'll talk about finite state machines in terms of languages and how these relate to parsing languages and recognizing words over a language. And then probably Wednesday we'll switch and talk about Turing machines. And Turing machines are kind of, the start of modern computing. They were a theoretical model for computation that, turned into all of the computers that we use today. They're all basically Turing machines. So we'll play with that, and this will lead us to our final topic, which will be a discussion of some of the theoretical aspects of computation, including limits on computability and P versus NP problems and the question of NP completeness. So we'll be doing a lot of cool stuff next week, and that'll round out our discrete structures course. All right, have a great weekend. I will see you next time. Thanks.